Hi, this is Barrett Gibbons, and in this video, I'm going to do the example of how we can derive the product topology on R cross R using the definition of a product topology. So the definition of a product topology when you have a cross product of two spaces is that the basic open sets in the product topology have the form of open sets from the first coordinate topology crossed with open sets from the second coordinate topology. In this case, we have X and Y are both equal to R. And so we're looking at the space R cross R, which is probably better known to us as just R2. Okay, so we're looking at the plane. And we want to think about the basic open sets in each of the two coordinates. So for X, the basic open sets are open intervals, A, B. And then for Y, the basic open sets are also open intervals, A comma B. So let's number these so I can distinguish the two kinds. So for X, I'll call them A1, B1, and then for Y, I'll call them A2, B2. And so the basic open sets in the product topology on R2 are sets of the form A1, comma B1 cross A2, comma B2. And these are open intervals, right? It's sort of confusing because we have open intervals here, but we also have ordered pairs because we're in R2, but these are open intervals, okay? Intervals, open intervals. So let's graph like a typical basic open set. I'm in the space R2. R2 or R cross R. And so I'm going to look at an open interval on the first coordinate. So I'll look at an open interval down here, something like that. And this would be my A1, B1. And then I'll look at an open interval on the vertical axis. That would be my A2, B2. And I want to look at all points X1, X2, where X1, I want to look at all points X1, X2, where X1 is between A1 and B1, and X2 is between A2 and B2. So the first coordinate has to be between A1 and B1, and the second coordinate has to be between A2 and B2. And I claim that that is going to look like this open rectangle. Okay, so those would be the basic open sets in the product topology on R2 would be open rectangles, open rectangles. And because just to check each point in this open rectangle, if I look at its x coordinate, sorry, if I look at its first coordinate falls between A1 and B1, and its second coordinate over here falls between A2 and B2. And so this would be the collection. My vertical line has gone a little off here. This should be sort of like a completely straight vertical line right here. Okay, so I didn't line those up quite as well as I could have. All right, but hopefully you get the idea. Okay, now you might be wondering, because we already have a topology on R2. We have the topology generated by open balls in R2. But now we have this new topology on R2, which we're calling the product topology. So this topology generated by open balls is what we call the standard topology. And then this topology with open rectangles is what we're calling the product topology. So how do these two topologies on R2 relate to each other? Let me draw a couple of pictures here. So the open rectangles look like this, and the open balls look like this. So an open rectangle is a rectangle with dotted edges all the way around it. And an open ball is a circle, not including its outside edge. And let's just, for ease of writing this clearly, let's call the topology generated by the open rectangles, let's call it T sub P for product, just temporarily, just for this video. And then we'll call the topology generated by the open balls, we'll call it T sub S for standard topology. Okay, so we have the product topology and the standard topology. How are these related? Well, I have a couple of claims to make here. So claim one is that every open rectangle is a neighborhood. I'm going to phrase that just a little bit differently, is a T substandard neighborhood of each of its points. And then claim two is that every open ball is a T sub product neighborhood of each of its points. So I'm claiming that open rectangles are neighborhoods in the standard topology, and open balls are neighborhoods in the product topology. Okay. I mean, we know open balls are neighborhoods in the standard topology because they're open sets. So they're a neighborhood of each of their points. We know that. So first, let's see why these two claims are true. Let's think about claim one. So let's think about claim one. Let me take an open rectangle for claim one. Let me take an open rectangle. And I want to say that it's a neighborhood for each of its points. So I want to take a random point inside of this open rectangle. Here's my filled in open rectangle. And I'm going to take a random point right here in the middle, or right here somewhere inside of it. Okay. And I claim that it's a standard topology neighborhood of each of its points. So being a neighborhood means it contains an open set, which contains that point. And in the standard topology for the open sets, the basis is the open balls. So can I draw an open ball? Can I draw an open set in the standard topology, which those are generated by open balls? So can I draw an open ball around that point, which stays inside of the rectangle? Yeah, I think I can. What I can do is I can just measure the distance from that point to each of the edges of the rectangle and take whichever one of those distances to the edge of the rectangle is smallest. In this case, it looks like the distance to the upper edge is the smallest in the picture that I've happened to draw here. And I can draw an open ball around it. And so that shows me that this rectangle is a standard topology neighborhood because I can put a standard open set, a standard basic open set, around each point, but still contained inside. Okay, so this shows me that claim one is true, this picture. Claim one, yes. For claim two, I want to go the other way. I want to take a random open ball and I want to show it's a product topology neighborhood. So I want to show that it contains an open set around each of its points. And I'll use a basic open set. And the basic open sets here are rectangles. So let me take a sort of a largish. Here's an open ball. Okay. And I'm going to take a random point in the middle of it. So something like here. And I want to draw a rectangle around that point. Actually, just to make my drawing slightly better, I'm going to make the point more towards the middle. If I get too close to the edge, things will get small. Okay. So I'm going to use I want to show that there's a rectangle inside of this open ball. So I want to show that there's an open set in the product topology, which that is to say an open rectangle, a basic open set, that is completely inside of this open ball. What I'm going to do to make that slightly easier is I'm going to draw a new open ball inside of this one, which has this point as its center. And we've seen in the past that that can always be done. So I'm going to make a smaller open ball that's contained inside of my big open ball, but that has this special point as its center. Okay. And then I'm going to look at the radii that go in the 45-degree angle directions in all directions. And I'm going to draw a rectangle through the points where those radii touch the circle. And there I've drawn a rectangle. In fact, it's even a square, which is even slightly better. I've drawn a rectangle inside of this smaller ball, which is inside of this bigger ball. And this shows me that claim 2 is true because I've shown that every open ball is a neighborhood in the sense of the product topology. So every open ball, if I take a point in it, I can draw a rectangle around that point and stay inside of the open ball. Okay, so every open rectangle is a neighborhood of each of its points in the standard topology. That means open rectangles are open in the standard topology. And then every open ball is a product topology neighborhood of each of its points. So that means every open ball is open in the product topology. So I have these two bases. One is rectangles and one is open balls. But what I see is that each rectangle is open in the ball topology and each ball is open in the rectangle topology. And what that actually tells me is that these two topologies are actually the same topology. It's two different bases, but they lead to the same topologies. Okay? So the product topology, we have a basis of open rectangles. In the standard topology, we have a basis of open balls. And it turns out that those are the same topology. So you can use different bases in different situations, depending on what will make the proof or the problem that you're trying to do easier. All right. Thank you for listening.